Hello. Is the human mind physical or not? That is it generated by the brain in some way? Or is it non-physical in its nature? Is the universe dualistic or not? For the first time, a scientist has proposed an experiment that may be able to distinguish this possibility. So, I'm Martin Thompson, this channel is Alpha Tucana. If you like this sort of vlogging about science and stuff, then hit the thumbs up button please. If you don't like it, hit the dislike button, I suppose, right? I prefer you to like it, obviously. If you're new to the channel, subscribe and leave a comment to let me know and I'll say hi. Now, philosophers and scientists indeed have been wondering for ever, it seems, about how can the mind possibly work, even if with the theory that it's generated entirely by the brain. There are phenomena which are completely puzzling. Consciousness, for example, doesn't seem like a physical phenomenon. But up until now, science has had no way to really get to grips with it. How could you measure something which is not physical? Quite a serious difficulty, right? We can measure brain activity, but you can't actually measure consciousness or the mind. René Descartes, way back when, proposed that the universe may be dualistic. There's a physical nature and there's a mind or mental or spiritual nature which is entirely separate. This leads to the puzzle of how does a spiritual or non-physical entity interact with the physical? How is that possible? Well, both theories have their problems. Okay, how is it possible for non-physical to interact with physical on the one hand, and how is it possible for physical to generate something like consciousness, which is rather not physical seeming at all, to say the least. So for the first time, a physicist, Lucien Hardy, at the Perimeter Institute of Theoretical Physics at the University of Waterloo in Canada, has proposed an experimental test. It uses quantum mechanics, and if this test violates the rules of quantum mechanics, then it suggests that the mind is non-physical. It won't be a total proof. It'll be very hard to prove that to scientists' satisfaction, let's face it. But it's a test proposed by a quantum physicist. That institute is a proper science place. Stephen Hawking is the distinguished visiting research chair there, so it's not like a random backshed college somewhere. It's a proper place, okay? And he's himself, Lucien Hardy is himself known for the Hardy's paradox or Hardy's theorem, which is in fact a proof of non-locality in quantum mechanics, relating to Bell's theorem about antiparticles not annihilating each other under certain circumstances, basically. So, he's up to snuff with his quantum mechanics. So I'm going to go through the test and Bell's inequality in a non-mathematical way, as best I can, and then we'll discuss the little tweaks to it that are needed, or one tweak in particular that's needed to allow us to test for whether the mind is physical or not. The test he's going to do is the test that distinguishes between whether quantum mechanics is right or whether classical physics is right in their descriptions of the universe. And this is based on Bell's inequality, or Bell's theorem. Bell's theorem says that no physical theory of local hidden variables can ever reproduce all of the predictions of quantum mechanics. Now, a theory of local hidden variables is what's known as a classical physics theory, a classical theory. The universe is made of dumb billiard balls and they bounce off each other and you can predict all their motions precisely if you can measure everything precisely enough. As we know, quantum mechanics is all to do with probabilities and randomness and stuff of that sort instead, and non-local variables. Local is something which is consistent with Einstein's theory of relativity. A local variable is one where we take into account the fact that things can communicate information between each other at below the speed of light. If it's non-local, then they are too far apart in space and time to be able to communicate with each other using known classical mechanisms like sending a photon between them, for example. That's non-local. Now, the way this is tested is in an experiment where we create a pair of particles, and they are entangled quantumly because they're created in a single event. So, for example, we might send a particle into an apparatus, say a diamond, and it will generate a pair of electrons with opposite spins, or some photons with opposite polarization, and those are directed off in opposite directions. But because they were created in the same event, until they interact with something else, they remain entangled. That is, effectively, it's as if they're kind of aspects of the same particle. At least that's a way of thinking about it. I think an actual theory of what is exactly going on doesn't really exist, and certainly not in a mathematical sense of providing a rigorous explanation of how it works. But we do know that when particles are created together as a pair, they remain entangled for a time, as I say, until they interact with something else and it gets all messed up. And we can therefore measure correlated properties between the two particles. And the interesting thing is that we can measure, say, the spin or the polarization at one detector, okay, and we can measure it at another detector. Because they're entangled particles, those results will be correlated with each other. So the way the experiment goes is we send these particles off to two separate detectors. Now they are separate in the sense that they are far enough apart that when we take the measurement on each particle, we make another measurement on the other particle at the same time. There's no time for them to communicate between each other. Okay, so they are separate. The experiments, the measurements are done simultaneously in the sense of Einstein's theory of relativity. Events are simultaneous if a photon could not travel between them, doesn't have time to travel between them, before event A and event B have both happened. So what we do, we create our particles, we send them to two separate labs, or two separate measuring detectors, which are ideally a good distance apart, because light travels very quickly. Okay, and then we make a measurement on this one, and a measurement on that one, and see if the results correlate. Now, if the particles are not entangled, the results are utterly random between the two. There's no correlation. So we have to deal with entangled particles so we can actually distinguish what the heck we're doing. So, for example, if we're sending electrons which have the property of spin, then we can measure, say, spin up in this detector. Then we know in this detector we're going to get a spin down 100% of the time. That is as long as the detectors are orientated the same way. Now, as it turns out, if say the detectors are, I'm trying to put my hands square to the camera, there we go. If the detectors are at an angle to each other, then we get different results. So if, say, this detector is upright and this detector is measuring horizontally the spin, then we might get, say, spin up on our electron in this one. But on this one, quantum mechanics and classical physics both predict a 50-50 chance of the second particle being measured as either up or down. And that's in fact what we measure. But the interesting bit comes when we put them at angles. So, at other angles than 90 degrees, that is. So, when they're both upright, we get 100% correlation. This will measure spin up, then this one will measure spin down. Same idea with polarization. Okay. or photons. I'm using electrons for the sake of it. The experiment is usually done with them or photons. So if we measure at 90 degrees, we might measure spin up on this one, and this one will measure one or the other with a 50-50 chance. If the detectors are at 45 degrees, we reckon basically what you have is a linear change, at least in classical physics, from 100% down to 50% down to 100% discorrelation, or 0%, the same if you like in classical physics. But at some of the intermediate angles, quantum mechanics and classical physics give different predictions. So at 45 degrees, for example, if it's going from 100 down to 50% here, then at 45 degrees classical physics gives you the prediction of 75% chance the same and 25% chance different. And at a 60 degree angle, classical physics gives you a 55% chance of the same and a 45% chance of it being different. But in both these cases, quantum mechanics gives a different prediction. Quantum mechanics at 45 degrees says it shouldn't be 75-25, it's going to be 85-15. And if the angle chosen is 60 degrees, then the odds are not 55-45, they are in fact 50-50. The reason for the different prediction in the maths is that in quantum mechanics particles are kind of waves, and they are described with wave formulae, and a wave is a sine wave, whereas in classical physics, when we're rotating the angles, it's a purely linear relationship. The probability goes in a straight line as we go along. But in quantum mechanics, it's a wave. Can I show it on the screen? Oh, there we go. It's a sine wave. I can't look at the screen and move my finger properly. Okay, there we go. And hence you get a slightly different curve. And the Bell's inequality tests for this. Furthermore, if the result differs between quantum physics and classical physics, there are two possible explanations in classical physics for why it might differ and save classical physics theory. One is that the particles are communicating with each other. Now we rule that out by moving them too far apart. Classical relativity tells us they cannot communicate at lower than the speed of light if they're too far apart. The light particle cannot get between them, between the times we take our measurements, to influence the result. So that is ruled out by the distance. The next one is that the particles are correlated because they knew all along what measurement they were going to give. Or there is some other variable in the experiment that we don't know about. Now, the point of Bell's inequality, which gives us this curved prediction, rather than the straight line prediction for the probability differences of our measurements as we change the angle, is that if there are hidden variables, you would get that straight line correlation. If there are not, you get the quantum mechanics prediction instead. And of course, what you get is what's predicted by quantum mechanics. So this rules out any form of collusion between the two particles. They don't know when they are created what they're going to be measured. They don't have a record of what the measurement is going to be before the measurement is taken. And when the measurement is taken, they do not collude with each other because they're too far apart to do so. So classical physics is ruled out. What's left is that they may collude with each other at greater than the speed of light, which is impossible in relativity, at least unless you fudge the logic a bit. Because relativity says that information cannot be conveyed at greater than the speed of light. Because if it was, what you would effectively be doing is sending information backwards in time. So what physicists are thinking is that, well, maybe this collusion does not represent information. One has to think about what the meaning of information is, and it's subject to definition, but it appears that because the initial measurement is entirely random, the particle does not know, in quantum theory, what the measurement outcome is going to be until it's happened. Until it happens, it's not predetermined, it's random. Then its collusion with the other particle at greater than the speed of light is not the sending of information, because it's random. Random is like the opposite of information. Information is systematic in some way. It may be something you don't know, but it's got some value. Whereas this is completely random, yet two particles are able to collude and cooperate. And this has been tested even with extreme cases, like in the two-slit experiment, where particles can pass across one side of a galaxy or another from a third one. The galaxy in between acts like a lens. Particles can come around this side of the galaxy or around that side of the galaxy to get to your telescope. And when you can see both of them, you see a particle come randomly here, then randomly there. You choose an object where the light is very dim and you're getting an average of, say, 1 photon per second from it, because it's we're really far away, billions of light years across the universe. And you get maybe a particle this side, a particle that side from the galaxy at random. But when you turn the telescope so you can only see one side, all the particles come from that side. And if you switch it, look at the other side, all the particles come from that other side instead. So they are colluding across time, or they knew billions of years ago how you were going to point your telescope. So the most likely explanation is that they are colluding backwards in time. Not in contravention of relativity, because this apparently is not information, because it's random. It's kind of, I think they're fudging it, and I think the philosophers are going to have to think about this a bit. But that's the explanation. So, how do we use this experiment to test for the human mind being physical or not? Well, when we're doing the experiments, in order to make life difficult for the quantum particles and their collusion, we determine the angle of each detector. Can I get them lined up? There we go. Determine the angle, whether they're upright or at their 45 degrees or 90 degrees or what, at random, each one, before taking the measurements. So they could be upright, 45, either one of them could be upright, 45 degrees, 90 degrees, or whatever, 60 degrees, before the experiment starts. So, or rather, at the time of the measurement. So it's quickly adjusted, take the measurement, take the other measurement, and we take the results of those experiments in which the particles got there and the two detectors were oriented to how we want. One of the, at 45 degrees or at 60 degrees, whatever we're trying to measure. But it's randomly determined on each run of the experiment, each particle pair, and we send thousands through. Okay. And that randomness is decided by a random number generator in a computer, which at the last instant sets up the detector at a given angle, and the particle arrives, boom, it's measured, and the same with the other one. Some angle is chosen, not at all related to what the other detector is doing. Just completely separate sets of measurements. Then afterwards the scientists go back over the maths and look at the results and line them up and take the pairs that are aligned in a way that they can measure the statistics from. Okay. And it backs quantum mechanics, okay? But to test for the mind and whether the mind is physical, the proposal from Lucien Hardy is that instead of a computerized random number generator, what we should do is at each location of each detector is have 100 humans wired up to EEG machines, and we'll take the noise from their brains, the EEG signals from their brains, and use that signal, those 100 people's signals, to generate random numbers to move the detectors. And he proposes that if the mind is in fact non-physical, we should get a result that violates quantum mechanics. because the experiments done up to date with purely mechanical random number generators, computers and stuff, do fit with quantum mechanics. We get the curved correlations rather than the straight line which classical physics would predict. Now, it might work. Nicholas Guyson of the University of Geneva, another physicist, a quantum physicist as well, has said he works in quantum cryptography and quantum communication, has a company called ID Quantique as well associated with the university, which allows businesses to have secure communications using quantum cryptography. So he knows his stuff there as well. He said that might work, but it might not produce much of a result. Instead, we should have the humans try to intend a particular result to the experiment and see if their intent actually makes a difference. So I think that could be interesting, and we will probably have to do both sorts of experiments and many times in different labs to replicate the results before people can really take the results seriously. I mean, even with the traditional quantum mechanics experiment, that has been replicated many times now to test that it really is doing what quantum mechanics says and not what classical physics says. And we would have to replicate this experiment many times. Many more times probably, because it's a tough one, philosophically speaking. But it's the first time we can have a physics experiment based on quantum mechanics and proper physics equations where a non-physical element is introduced into the experiment, the minds of people. Or if it is non-physical, it should produce some sort of error in the experiment. That's the idea. Now, parapsychologists have been measuring weird phenomena with the human mind obviously for a long time, and although the results are quite interesting, it's not based on rigorous physical theory. It's empirical purely. Just the measurements are there, the results are peculiar. I'll refer you to a couple of books, but they are not based on maths and an equation. And this is where science really shines, is if you can produce a theory and some maths to back it up, and that makes predictions about what should happen, and then you do the experiment, you know you're onto something. So we've had these psychic phenomena experiments for many years now, which are definitely showing the mind influencing something. I think. Other people might say, no, it's nonsense. But here, for the first time, we have actual equations making predictions. And those predictions, because we've done the experiments without mental influence, if we do the experiments with mental influence and we get different results, we know we're onto something. The books of the psychic phenomena I would suggest are The Conscious Universe by Dean Radin or Radin. I'll put a link in the description. And also Irreducible Mind by the Department of Perceptual Studies at the University of Virginia, or the people in it, who've been studying how the mind cannot be physical. At least when you look at it philosophically and scientifically, it doesn't make a lot of sense from a lot of different angles. It's certainly problems which need to be solved somehow. So this experiment, when it's conducted, or if it's conducted, hopefully it will be, or something like it, may, for the first time, distinguish whether the mind actually is physical, generated by the brain, or whether it is something more than that. It'll be, if the result is positive, then that'll be the most important experiment in the 21st century, I'm sure, and possibly the most important experiment conducted ever. However, we might get a null result, and what does that mean? It might mean the experiment needs to be conducted more carefully, or we have to think of another angle. But it's the first time, really, that science, in the sense of hard science with mathematical theory, has had a chance to get to grips with the non-physical and see if it messes up the results or not. So what do you think? Could it work? What if it does? What does it mean? What if it doesn't work? What does that mean? I'm interested to hear what you think, so leave a comment, and I'll see you in another video sometime. Okay. Bye for now.